Hello everyone, and welcome to the Mathematecker channel. Whether it is to study exact science, make statistics or trades, or to measure weights, distances, or time, numbers are present in our day-to-day life. In mathematics, the abstract notion of number finds its roots in the idea of quantifying objects, and quantity can vary from so small microscopic amounts of things to huge amounts on a macroscopic scale. This is why, when it comes to represent a number, many mathematicians struggled through centuries to find an efficient way to do it. Proposing a numeral system is giving a method that allows us to write numbers by using limited number of symbols. Nowadays, when thinking about numbers, lots of people can imagine the appearing sequence of symbols. In fact, whether it's a basic natural number, an integer, a rational, a real number, or even a complex number, the symbols we're accustomed to use are always the same. 0, or 1 or 2, or 3 or 4, or 5 or 6, or 7 or 8, or 9. Those are nothing more than 10 symbols that we use to represent our numbers in our day-to-day used positional decimal numeral system. In this case, the number 10, which equals the number of symbols from 0 to 9 that we have in the decimal numeral system, is called the base of this numeral system. As for the used concept of numeration, it is the numeration by juxtaposition, where the order of the position of each digit determine the power of 10 by which this digit is multiplied. Yes, for example, the scripture 987 means 9 multiplied by 10 to the power of 2 plus 8 multiplied by 10 to the power of 1 plus 7 multiplied by 10 to the power of 0. So in our scripture, 987, the digit 7, which is in the first position from the right, is multiplied by the 0 power of 10, which means that it is multiplied by 1. So we have 7. As for the digit 8, which comes in the second position from the right, it is multiplied by the first power of 10, which equals 10. So we have 8 multiplied by 10, which equals 80. And finally, the digit 9, which comes in the third position from the right, is multiplied by the second power of 10, which equals 100. So we have 9 multiplied by 100, which equals 900. Therefore, we have the sum 900 plus 80 plus 7, which equals 987. Let's now see the general principle of the positional numeral system. For every natural number capital N, which is strictly greater than 0, and every natural number x, which is strictly greater than 1, there is one and only one expansion of the number capital N, according to which capital N would be equal to an multiplied by x to the power of n plus an minus 1 multiplied by x to the power of n minus 1 plus so on until a 1 multiplied by x to the power of 1 plus a 0, such that the numbers a0, a1, and a2 until an are natural numbers strictly lesser than x, and an is different from 0. Let's see a proof of this proposition. As we've seen in one of the previous published videos, the Euclidean division of capital N over x give us one and only one pair of natural numbers that we can note q1 and a0, such that capital N equals q1 multiplied by x plus a0, with a0 strictly lesser than x. And since this pair of natural numbers, which is q1 and a0, is unique, then this expansion of the number capital N is unique. Now, by doing the Euclidean division of q1 over x, we find that q1 equals q2 multiplied by x plus a1 with a1 strictly lesser than x. This means that capital N equals q2 multiplied by x plus a1 all multiplied by x plus a0, which equals q2 multiplied by x to the power of 2 plus a1 multiplied by x to the power of 1 plus a0 with a1 and a0 strictly lesser than x. And again, the unicity of this expansion result from the unicity of q2 and a1 as quotient and rest of a Euclidean division and the unicity of a0. So when going through this process of expansion by successive Euclidean divisions until we reach the quotient 0, and by writing the last quotient different from 0, as an, at the end, we would have done a unique expansion of the number capital N in accordance to the statement of the proposition. Let's now see some mathematical notation about numeral systems. If capital N equals an multiplied by x to the power of n plus an minus 1 multiplied by x to the power of n minus 1 plus, so on, until a 1 multiplied by x to the power of 1 plus a 0, such that the numbers from a0 to an are strictly lesser than x natural numbers, and that an is different from 0, then we can write the number capital N as equal to the highlighted juxtaposition of the numbers from an to a0, or just the juxtaposition of the numbers from an to a0. And in this case, we would have written the number capital N in the numeral system of the base x. Let's see some examples. In base 2, the number 10 is equal to the highlighted juxtaposition of the numbers 1, 0, 1, 0, or just 1, 0, 1, 0. As for the number 2, it is written in base 2 as equal to highlighted 1, 0, or just 1, 0. Let's now see how to convert a number scripture from one base to another. If capital N is a different from 0 natural number, which is written in the numeral system of base x, such that x is strictly greater than 1, and y is a strictly greater than 1 natural number, then, in order to write capital N in the numeral system of base y, we must, at first, write the number capital N in the base 10, and from there, we write it in the base y. Let's see an example. We have the number capital N that is written in the base 4 as the juxtaposition of the numbers 1, 2, 3, and 1, and we want to write it in the base 5. This means that capital N equals 1 multiplied by 4 to the power of 3, plus 2 multiplied by 4 to the power of 2, plus 3 multiplied by 4 to the power of 1, plus 1 multiplied by 4 to the power of 0. That equals 1 multiplied by 64, plus 2 multiplied by 16, plus 3 multiplied by 4, plus 1 multiplied by 1, which equals 109 in the base 10. Now, in order to convert the number 109 to the base 5, we do the successive Euclidean divisions of 109 over 5 until we reach the quotient 0. As it will be shown in the appearing figure, by doing the Euclidean division of 109 by 5, we find 21 as a quotient and the number 4 as a rest, which will be multiplied by 5 to the power of 0 in our base 5 numeral system. Then by doing the Euclidean division of 21 over 5, we find 4 as a quotient and the number 1 as a rest, which will be multiplied by 5 to the power of 1. After that, when doing the Euclidean division of 4 over 5, we finally reach 0 as a quotient and the number 4 as a rest, as 4 is strictly lesser than 5. We therefore deduce that 109 equals 4 multiplied by 5 to the power of 2, plus 1 multiplied by 5 to the power of 1, plus 4 multiplied by 5 to the power of 0, which mean that in the numeral system of base 5, 109 is written as equal to 414. And this means that our main number that was written as equal to 1, 2, 3, and 1 in base 4 is written as equal to 414 in base 5. So, that was an overview that can serve as an introduction to the domain of numeral systems. We hope that it has given you a good insight about this topic. And if it is the case, we invite you to subscribe to our channel and to like and share the video. You can also write some remarks you may have in the comment section below. We will be making other videos about this in the future, and until then, we wish you the best.